Hi, it's Robin. We'll be figuring out how to program the C64 to read this Atari Touch Pad today. But first, I want to explain what motivated this episode. If you don't want to hear about it, check the description for a time-stamped index to jump ahead. I was reading about how the second-last Zellers store in all of Canada would be closing this week. And that got me thinking about all the stuff I bought there over the years. If you're not familiar with Zellers, it was one of my favorite stores when I was a kid in the 1980s. It was a discount department retailer, kind of like Kmart or Walmart, but to me, it somehow had more appeal, more mystique, more panache. I'd never know what I'd find there, and they seemed to carry more 8-bit stuff than any other store, and usually at the best prices. The first Zellers opened way back in 1928 by Walter P. Zeller, and it reached a peak of 350 stores across Canada in the 1990s, but it rapidly lost ground once Walmart entered the Canadian market. They sold many of their store leases to Target and closed most of the remaining stores in 2013, and now there's just a couple remaining. Well, Zellers is where I bought my first data set for my Commodore 64, and it still has the price tag, $49.99 Canadian, and that would have been in 1984. It's also where I bought my Commodore 64 Programmer's Reference Guide, although I don't think it was this copy. My original is really beat up and is missing the cover now. And once I got a disk drive, it's where I bought my first disc game, Hitchhiker's Guide to the Galaxy. And I still have all the stuff, like the piece of fluff. And one time a friend and I rode our bikes to Zellers, probably summer of 1984, and there was this huge bin of Epix games for just $10 each. But on closer inspection, it was only 2 different games, all Gateway to Apshai or Jumpman Jr. So my friend bought Gateway, I bought Jumpman Jr., and those were 2 of our favorite games. For the longest time we would trade them. Unfortunately, in the late 90s, I got rid of a whole bunch of the boxes for my games, needing to make space, and I've regretted it ever since. I didn't get rid of the actual games, and some stuff did survive. And it was also at Zellers that I first saw the Mastertronic games, and bought Master of Magic, one of my favorites, The Last V8. I think that's a tiny bit of price tag still left on it there. And Sika of Asiya. And as far as I know, it was Zellers who first brought Mastertronic titles to Canada, and sold them for $10 each, which was pretty amazing compared to the other prices around. But besides the more mainstream 8-bit stuff, they also brought in more obscure stuff if they could sell it cheap enough. For example, I bought C64 games on cassette there. This one, The Tombs of Cheops, is a text adventure game. I love this. A real action shot of the game. This artwork, and what I guess they're referring to that tiny little screenshot there of a text adventure. Pretty hilarious. Another one for that same company is this very rare Deflector. Note that's a different game. You might know the Deflector with a K. This one's with a C. It's not a particularly good game, but it's rare. And that was all from this company here, Lane Marketing Limited. You could also get Blank Media there from cheap no-name brands. And I just bought this late last year when I saw it was a Zellers branded Christmas album. It was terrible, but I enjoyed every minute of it. But probably the most infamous 8-bit thing about Zellers was that they sold a line of pirated cartridges. They all have the same black label and white lettering, and they have this bizarre art on them. That's like Ghostbusters, even though the game is not Ghostbusters. Circus, Dragon Treasure, Earth Attack, Radar, Time Warp, Pinball, Busy Police, which is a total ripoff of Keystone Capers, which coincidentally was just ported to the Commodore 64 in the last month or two, and the awesomely named Ocean City Defender, no idea what the art's about there, which, can you guess it, is a clone of Atlantis. Ocean City Defender, kind of the best band name ever, and in fact a friend of mine, that is the name of his band. Might want to check them out. By the way, all those pirated carts, I didn't buy them new at Zellers. I picked them up later at thrift shops. Then one time, I went in, there was a huge bargain bin full of many copies of Star Raiders in this large box. All priced to clear at $1.97. I think this was the height of the big video game crash. Now, I didn't even have an Atari 2600, But when I looked and saw, it included not only the Star Raiders game, but also included a comic book and a controller. I thought, I have to have this. So it's still in pretty good shape. I think I bought this almost 36 years ago. So it includes 2 boxes inside. There's the Star Raiders game, which includes the cartridge and the manual, and Atari Force Comic, issue 3. And this set off a real love for Atari Force. I've got all 5 issues that were packed in with Atari 2600 games. And when they released kind of a second generation of Atari Force in full-size comics, I collected all of them, including the final special issue. And on top of that, like I was saying, it includes the Video Touch Pad. And here it is with the Star Raiders overlay, which can be removed. So this was released so that the Atari could also have a control pad like this ColecoVision or the Intellivision also had them, which allowed for more complex input for games. Beyond just the single joystick button and 4 directions, it gave 12 extra keys that could be used. Star Raiders actually only used 5 of them. And even stranger, Atari never did release another game, as far as I know, that used the Video Touch Pad. Although they released 2 other controllers that were physically identical with different names, called the Atari Kids Controller and the Atari Keypad. But I don't have either of those. So way back in 1984, I thought it'd be interesting to see if I could get this working with my Commodore 64. I wasn't successful, so I put it back in the box and mostly forgot about it. And every once in a while I would think about, when Zellers would come up in the news, I would think about this one unresolved idea from Zellers. And with this store closing, it made me think, I want to try and finally figure this out. So that's what we're doing today. In the Programmer's Reference Guide, Appendix I, it shows the pinouts for input and output devices. And that includes the joystick port here. It's identical for both control port 1 and 2. And basically there's 9 pins on the joystick. Pins 1 through 4 are up, down, left, and right. And then pin 6 is the fire button. And pin 8 is ground. And that's all that's normally used on the C64. So normally the 4 direction pins and the fire button have 5 volts, they're high, and then they get grounded when the switch is closed. So I've got my multimeter hooked up pretty terribly here. Some little jumper wires on here. In the book here, this is looking into the control ports, so it goes from 1 to 5 and 6 to 9. But here on the end of the joystick, it's the opposite. So this is pin 1 over on the right, and then this would be pin 8, which is ground here. So I've got direction up and ground, and I've got my multimeter set up with the continuity mode. And so if I move the joystick up, you can hear it sounds. But now the other directions work and the fire button doesn't do anything. By the way, this is a Trooper joystick by Hyperkin. This is a brand new Atari and Commodore compatible joystick that I bought on Amazon. It's actually pretty good. It's got a really long cord on it. Okay, and we can just move this jumper. Pin 2 is down. You see? And so on, and we'll try the fire button here. So, nothing there. Alright. Okay, so just to show what I did way back in 1984 was just hopefully printing the contents of 56320, which is the CIA. So the program's just repeatedly printing out. I'm plugging the joystick into port 2. Yes, while it's turned on. You see if I press the fire button, the number drops by 16. That's 2 to the power of 4. If I push up, that's 1, 2, 4, and 8, corresponding to the 4 directions. I'll unplug the joystick and plug the Video Touch Pad in, and now we'll press those buttons. No effect. So what's the deal? I tried everything I could think of as a kid. Well, that was about it. So I gave up. But what I know now is that while Joystick is going to read the controller all his inputs on the CIA, I know that the Video Touch Pad actually needs to be sent. We have to configure the input-output chip to actually output the 4 bits from the what's normally the joystick up, down, left, and right. We have to configure those to outputs to select the row that we're going to scan. Okay, so I'm going to select the first row, and it comes back through the fire button. There, so pins 1 and 6. And that is this button here. You see the other ones don't sound it. Okay, and if we select the second row, that's pin 2. That's that button. And so on. Here, we'll jump to pin 4. So we know we can read this column. How do we read the other 2? Well, in addition to the fire button, we also have available these pot AX and pot AY lines. Those are actually used for the paddle controllers. In this case, they happen to work for this as well. Okay, we'll select pins 1 and 5. So that's row 1 and column 1 on the pot AY line, and pot AX is on pin 9. Okay, and again we can do the same thing. We can select the second row there. We can use this knowledge to program on the C64. So I'm just going to change that to line 20. And line 10, I'm going to poke 56322, which is the corresponding data direction register. If you poke it with 0, that means everything is an input. You might expect 0 to be output and 1 to be input, but in fact it's the opposite. So those low 4 bits we want to set to outputs. So we do that by poking, 15. And now we will go to 20. So we'll try listing that, and we will run that. And there we have a bit of success. We got some numbers wiggling there. Okay, so that's promising. But there's a major problem. Since we configured the CIA chip to have outputs, that's affected the keyboard scan routine, and we've lost control of the computer. So we gotta reset here. So we'll jump ahead here. Here's the final version of the program. This poke turns off the kernel interrupt that scans the keyboard and does some other things, because it actually interferes with reading. And then down here on line 50, we turn it on before each loop. Correspondingly, here's where we set the data direction register so that the low 4 bits are all outputs, and here is where we set them all to outputs, as that's what the kernel routine expects. And then the space in below, we're actually going to call it 4 times, once with 14, 128, plus 14, I'll get to that 128 in a moment, and this is where we're going to select which row we're looking at. Now, the number 14 might look a bit confusing, but in binary, that is actually 1, 1, 1, and 0. The next line, 13, 11, and 7. In binary, those are 1, 1, 0, 1. That's 14, 13, 1, 0, 1, 1 is 11, see the pattern here now, and 0, 1, 1, 1 is equal to 7. So what we're doing is, for those 4 output bits, the low nibble, we are selecting which row we're going to scan. So when you choose 14, that's the first bit is 0. That means we want to scan this row, then this row, and then this row. That's what those values are. And the reason we're adding 128, that is to set the high bit. And we're doing that because that's actually another special case. To read that pot X and pot Y line, these pins, those are actually analog values. The voltage can vary all the way from 0 up to 5 volts. That's actually sent to the SYD, which does the analog to digital conversion. It changes that voltage into an 8-bit value from 0 to 255. There's only 2 registers in the SYD that can read these pot AX and pot AY and also pot BX and BY. So to handle all 4, you can actually choose which control port is sent to the SYD. So for now, we're just going to be actually, I keep saying AY, but actually it's this control port 2 that we're using. So it's sending pot BX and BY off to the SYD. After we select the row we want, then we go sub 80, and we're going to print out the values. These 2 are from the SYD. That's reading pot Y, X, and here we are reading the joystick port. That's the fire button. Okay, we'll try running this program. I know it's ugly. You see how if I press the top left button, now the number has changed to 255 there. So the pot X and Y values are being read properly now. And I can press up here, and those are going to drop by 16 down the bottom right corner there. So that's really ugly, but we do have it working. Now we're going to write an assembly language version that should work a lot better than this. This is just our proof of concept. Okay, and now I have Turbo Macro Pro started up, and let's go through the code quick here. So we're going to assemble this to location C1000. It could be anywhere, but I wanted this to play nice with BASIC, so that's why I've chosen it. Note that to assemble to high memory like that, we have to use the REU version of Turbo Macro Pro. I have my REU plugged in here. If you're using Vice, you can also do that even if you don't own an REU, but if you're using an emulator, or if you're using the C64. In one of my previous videos, I showed how to hack it to enable the REU. And just for ease of assembly, I go back arrow and 3, and if I start the code, it just goes to basic and exits cleanly here with the ready. And I can hit sys 320 to re-enter. That's what this RTS does. One thing Turbo Assembler doesn't do very well is when you try to code with BASIC, it doesn't have a quick way to assemble and drop into BASIC. So this is just a little hack to put this RTS here. And I've put a note here that when I'm done testing this, I want to assemble what is probably my final version to disk. I'm going to remove that RTS. It's just a way of dropping the BASIC, and the RTS returns control to BASIC instead of executing the code. And here I have a storage byte. After we're done our key scan routine, we're going to store the value in here. 0 means no key, and otherwise keys 1 through 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this is just where we're going to store it in memory in a known location at 49152, assuming we remember to remove this byte, or 49153 if we don't. That could go anywhere in memory, but to me it seems tidy to leave it at the beginning. It's in a known location then. And this is the routine that we're going to call when we want to call the scan. This is the location, which is going to be 49153, assuming again that we remember remove that return. So we're going to disable interrupts, and we're going to store the current value of the data port and the data direction register, because we're going to be overwriting those, but we want to set them back, clean up after ourselves so that BASIC isn't bothered by it. And we're just going to save those in these memory locations I labeled old DC100 and old DC02, and those are just down here at the bottom. There they are. And like we talked about before, we want to set the low nibble of the data direction register, the low 4 bits, to outputs so we can choose what row we're going to scan. Now this is the actual scan routine. We're going to be using X as a counter for what button we are checking currently, numbered 1 through 12. And we're going to initialize the result. And we're also going to keep track of the column count, because we've got some looping to do here, and we don't have enough registers in the 6510 to do it without storing some in memory. So we're going to loop through all 4 columns. First, we're going to load Y with the current column count, which is 0, the first time through. And then we are going to load from this table I made called column. That's down here at the bottom. And you might recognize these values from the basic program. These are the outputs to choose what column we're selecting. Column 1, 2, 3, and 4. Or if you want to number them 0 through 3, that's fine. And here we are directing the control port 2 that we're using to the SID by setting that bit to 1. So now that we've got the value from the column indexed by the column count, we're going to store that in the data port to choose the column. And now we're going to have a delay here. Now we actually have to delay many cycles to accurately read the paddles, or in this case, just to read the button. So that's 128 times, what is that, about 7 cycles? So 7 times 128. So we're delaying 900 cycles, and that's necessary. It's not really a flaw in the C64. The Atari 2600 does it as well, that when you want to read a potentiometer, the way it does the conversion takes some time to convert that voltage into a number. We have to wait to get a valid value back. And once that delay is done, we increment X to show that we're now trying to read button 1. It goes from 0 to 1. And we're reading pot Y from this SID register. And if the high bit is not set, that means if it's plus, we just jump ahead to this ahead 1. These pots return a large value, probably 255, but at least above 128 when they are pressed. So if we did detect a button press, then we're going to store that number 1 in the result. And we'll still keep going. Now we're checking button 2, increment X, and check pot X for a button press. By the way, the C64 GS introduced a 2-button joystick, and they use the same technique of reading, I think it was pot X, and actually it could do a 3-button joystick by also reading pot Y. And again, if it's a positive number, meaning below 128, then there's no value. Otherwise, we're going to update result with button 2, that we've pressed button 2. And you notice that this can only detect one number, and the highest number takes priority. Maybe this could be coded smarter, but to try and detect multiple buttons, but of course not every combination would work. Okay, and then finally we increment to button 3, and we check to see if the fire button is pressed. We're checking for a value of 16. That's because it's bit 4, the 5th bit. And we have to check that, and if it's not equal, then we go ahead, otherwise we store the result. Okay, now we have scanned a full column. Now we're going to increment the column count and check, have we checked 4 columns? If not, then we loop through this again, and again update, get the new value for the second column, and select that column, and do the same thing again. Again, delay to read from the SID, and just continue through. And finally, we restore the old values that we had stashed away so that we're not interfering with BASIC. We re-enable interrupts so that the keyboard scan can continue, and we return. And that's it. Pretty easy, eh? I'll just comment out that line, and to assemble to disk, we go back arrow 5, and we'll call that ASM9.0. That's assembled. Okay, we're back out in BASIC. Now we can load the machine language routine that we just wrote to disk, ASM9.0. And you should always type new after you do that. And I've got a basic program I wrote here. Okay, let's list that. Okay, and let's go ahead and run it, and then I'll explain it after. Okay, so it just shows a little dial pad, and kind of like a phone. You press the button you want, and it highlights the button. There we go. What am I doing? So there they all are. And like I was saying, if you press 1 and 3 together, it shows the highest value. If I choose 4 and 9, it'll do 9. If I choose 0 and the hash beside it, yay! Goal accomplished. Okay, let's look at this program. All it does is it clears the screen, and it prints out the little dial pad. Then it makes an array with 13 elements from 0 to 12. And here, we're just doing a little loop for each row, 0 to 3, for each column, 0 to 2, calling them X and Y. And it does a little bit of math here, where we're multiplying the Y value times 3, adding in the X, and then adding 1. This is just linearizing. This is a way when you have a two-dimensional grid and you want to write that into a single-dimensional array, we frequently do this kind of math. So location 1065 up in the top corner, this is 1024, and this is 1064, and this is 1065. So we're starting at this location, and then for each extra Y value, we're going to multiply that by 80. We just want the screen location of this grid. So we're moving down 80. There's 40 column screen, down 2 rows is plus 80, and then whatever X value, 2 at a time as well. Okay, so basically we're just making an array of screen locations, or for values from 1 to 12, and then we just complete that loop of generating that table. We call our machine language routine at 49153. So continuing on from line 200, we call the machine language routine, say that the last key pressed is equal to K, which is just 0 the first time, but then K gets the value from the machine language routine that we stored, and it's going to be from 0 to 12. And if the last key is equal to the current key, then we're done. We're just going to, well, we're not done, we're done that loop. We're just going to call it again. We're just waiting for a key press change. If the last key was not 0, that means it was not a non-press, then we're going to poke that screen location and clear the high bit, which is what allows the screen reversal. And otherwise, we are going to OR 128, which is setting the high bit to make that reverse location appear. So this is just the logic that makes the screen, when we press the button, it is just toggling the high bit on or off. So that's what this extra little bit of logic is here. That's why we're keeping track of last key. Okay, boy was I ever long. That's it for today. Special thanks to my patrons who support me in making these videos. Many of their names are scrolling by on my C64 right now. If you haven't already, please consider subscribing to the channel. And if you want to be notified of future videos, click the bell icon. Thanks for watching, and we'll talk to you next time.